Welcome to CON323, AWS App Mesh under the hood. My name is David Bell. I'm a senior software engineer at Amazon AWS, or AWS. I've been at AWS for about 4 years now. I spent the first 2.5 years working on an ECS, the Elastic Container Service, and I've spent the past 1.5 years building a new service called AWS App Mesh. AWS App Mesh is a managed service mesh offering, and it does what container orchestrators like Kubernetes and ECS do for your compute, and applies the same concepts to your network. Now, before I get into what this talk is about specifically, I want to talk about some things this talk isn't going to cover, and some talks you might be interested in seeing if you're interested in that kind of thing. Sorry. The first, Containers 216 and Containers 209. Those talks will cover getting started on App Mesh and integrating App Mesh into your observability story, whether that you're using X-Ray, CloudWatch. Containers 406, done by my colleague Brian, will cover both our idea of a customer's journey of adopting App Mesh, starting with their existing infrastructure and migrating it into their mesh, as well as customer experience from Chick-fil-A, leveraging Flagger on EKS to manage their services in production. Finally, AWS App Mesh uses Fargate extensively. We use it for almost everything that we do. And I highly recommend you go to Containers 423, AWS Fargate under the hood. I saw a dry run of this a week back, and it's just amazing. And I remember when I was on the team when we were designing Fargate and the work that went on into it to be able to allow you to launch serverless containers at scale. Lastly, Containers 421, EKS under the hood. EKS is a very interesting service. It's sort of a control plane for control planes. And I think the challenges that they have to solve are very interesting and unique. So what does this talk about? So at Amazon, we're a very document-driven culture. This is actually probably one of 5 PowerPoints I've had to do. And the reason for that is it's very easy to convince yourself you understand your problem with a few slides and some bullet points. Whereas when you write it down as a document, you have to define a narrative, and it forces you to think clearly about what your problem is and what your solutions are. We take those documents, and during meetings, we spend the first 10 to 15 minutes reviewing the document. For some individuals, they're able to really dive deep into a particular section. Others are looking over the whole document, combining it together in their mind and understanding the whole problem. And then we spend the rest of the meeting discussing that document and allowing it to drive the conversation. When we're building a new service at Amazon, like AWS App Mesh, we obviously write a lot of design documents, new features, APIs. But one of the most important documents we write is the principal design document. It's a roughly 10-page covering every aspect of that service, from the overall user experience, what our customers want and how we're going to give it to them, to the technical design, system overview and the technical implementation, as well as how we're going to scale those services over time, as well as the operability and maintainability of that service. Because remember, at AWS, we're not just building services for the next year, we're building them for the long term. And so we want to ensure that we're able to maintain those services and scale them and add new features for as long as we for as much as possible. Sorry. So you take this document and you schedule a principal design review, and you review this document with 5 to 10 principal engineers at Amazon, people who were there at the beginning building some of the most foundational services of AWS, services like EC2, S3, DynamoDB. And their job is to tell you what you missed. Maybe it's something in your API. Maybe you think you've designed things in such a way that makes sense, but when you start adding features, you're going to hit some roadblocks. Or maybe it's a part of your technical implementation. Maybe your solution to scaling doesn't actually scale all that much. They have the experience to tell you what you should go back and fix so that you can design a better service that can be maintained for the long term. So today what I want to do is actually walk you through our principal design document, starting with working backwards from the customer needs, then discussing our system design, and finally talking about how we operate App Mesh at scale. So first, let's talk about working backwards. At Amazon, we always start with the customer. And to stretch the analogy of this talk a little bit, it doesn't really make sense to talk about what's under the hood of a car until you understand what car you're building. You might have a commodity car, luxury sedan, or an exotic sports car, and all of those experiences are fundamentally different with different trade-offs. So, first question we always ask is, what kind of car do our customers want? Obviously, talking about a networking product, they want routing. Pretty straightforward. We're talking about things like layer 4 routing, TCP, UDP, as well as higher level layer 7 routing, HTTP-based, so things like path-based routing, headers, also internal details like retry strategies and timeouts, ensuring traffic is retried on failed requests, and that in the event that an individual request is taking too long, we short-circuit it rather than letting it sit in the system. And once we've decided on a set of targets, load balancing that traffic across those targets. Our customers want observability, and not just service to service, but considering the entire request. It used to be, typical application might be, customer makes a request to your front end, then that request goes to your back end, and then to your database. So roughly 3 hops. Now we're seeing customers with dozens of microservices. And one customer request might fan out into dozens of secondary requests, and those can fan out further. So when you're thinking of any individual customer request, you need to understand the entire call graph and be able to debug it and find slow or failing request paths. Our customers want security. So this is both encryption in transit, ensuring that all communication within your mesh is encrypted from each endpoint. But it's also things like authentication, ensuring that you know your clients. Additionally, it's authorization, being able to say exactly what individual identities can do with your service. And lastly, they want transparency. I think this is an interesting topic because it doesn't actually come up too much in conversation with customers, but it's something they really want. A motivating example for what I mean by transparency is, let's say you have a load balancer, and you have 9 tasks behind that load balancer. And let's say one of those tasks is just failing, and you thought your health checks would cover it, but they're not. So every request that hits that task, 500s. Now, from your perspective, you can clearly see from your logs, hey, this service is just hard down. But from your customer perspective, they just see that 1 out of 9 requests randomly fails. And they don't know if it's one bad host that they're happen to hit 1 out of 9 times, or if maybe that's actually just your SLA. Now, that's an okay trade-off when you don't know your clients, but more and more, the majority of service-to-service communication is happening between services that are within your organization. And because of that, you have a certain level of trust and desire to maintain performance between those endpoints. So when we talk with customers, what they're really looking for is no middle boxes. Basically handling all of these things, routing, observability, and security, in such a way that from a network perspective, everything is happening point to point. And of course, because it's AWS, customers want to tell us what they want to do. They want to declare their intentions through an API, and then leave it up to us to handle the heavy lifting and implementation of their intent. So let's start with how do we handle application traffic? What I have up here on screen is a rough approximation of an ECS task. We have 2 containers, an application container and a sidecar container, might be a metrics agent or maybe a logger. And then we have this task boundary, and that represents compute, so a virtualization boundary, but it also represents a network boundary. For those applications sidecar, they communicate out over a common network interface to the cloud, and they receive traffic in the reverse direction. Now, as I said, our customers don't want middle boxes. So if you're guessing that whatever our solution is fits in that box, you're probably right. So what we do is we deploy a proxy with every application, either ECS task or Kubernetes pod. And we can start by just deploying a proxy and changing applications and sidecars to talk through that proxy, to become mesh aware. And that's all right, but it has some real downsides. Change your application code. Maybe it's configurations, if app mesh, talk to proxy, otherwise do the normal thing. But even worse, you can't always change the code. There are lots of people running sidecars that they receive from third parties, and it's a hard sell to convince those third parties to make them integrated with app mesh. And so what we want to do is we want to remove these roadblocks and allow transparent proxying for our customers. And so we did that by leveraging a Linux kernel primitive called IP tables. IP tables allow us to capture TCP and UDP packets coming both from applications and the cloud and route them directly into the proxy. This ensures that we transparently proxy all customer traffic, both inbound and outbound, and ensure that it's valid. And then we can perform things like load balancing to distribute it to endpoints out in the network. So now that we understand how we're going to handle application traffic, what's that API that configures it? And APIs tend to seem like they're very simple. You spend a few hours, you set it up, you define your Swagger spec or maybe your proto buffs, and you call it a day. But APIs are actually one of the hardest parts of a service because it's the only thing you can't really change. At the end of the day, if something's not working for us, we can always build a new service and replace the implementation. But APIs are where our customers integrate. And so we want to make sure we got it right. And after a lot of discussion, we came up with this application-centric network model. And what do I mean by that? Typically, when we talk about networking, we're talking at the level of a VPC. So we say, I have some subnets, and they're assigned CIDR ranges. I have ports and security groups. And while it's important to understand that so you can debug network issues, it's not the level we think at in our day-to-day. How many people, when they're integrating with a new service, think about the CIDR range that service lives in? And what we realize is there's this very common pattern. At the end of the day, you have some traffic source, some client that wants to talk to a service. Then you discover where that service is using your service discovery mechanism. Maybe it's DNS, maybe it's some managed service discovery service. That service discovery system typically routes you to a load balancer, which handles that layer 4 and layer 7 routing, and distributes requests across traffic targets. And so we decided to take this model and bring that to the forefront in our API. So starting with that client, we define a virtual node. A virtual node represents the source and destination of all traffic in your network. As a source of traffic, it explicitly subscribes to the services that it's interested in. Not only does this allow us to scale in terms of the amount of configuration we distribute to customers, but it also provides a little bit of defense in depth. If you don't want a node to be aware of how to talk to a service, you just don't let it subscribe to that backend. And that ensures that it doesn't receive any of the configuration necessary to talk to it. Next, we define a virtual service. And a virtual service is a lot like DNS. It's this logical pointer that ties a friendly name together into something that you can actually send traffic to. But DNS doesn't really tell the whole story, right? You might be using A records, so you query DNS and you get a few IP address back. Maybe you're using SRV records, so now you have some dynamicism on ports. But it doesn't tell you how you have to talk to that service. It doesn't tell you, does it do TLS? What ports does it talk on? How do you route through it? And so rather than just giving you an endpoint, we actually provide a whole implementation with our virtual service. And that implementation is a virtual router. And if you're familiar with the ELB, ALB, NLB APIs, it's going to look very familiar. You can define your inbound ports, a set of routes that can match on traffic based on things like headers and path. And additionally, you're able to define actions that cover things like retry strategies, timeouts, and then finally, obviously, routing to a set of targets. Then, on the other side, you have those virtual nodes. So as a destination for your traffic, they tell you exactly how to talk to that service, primarily through ports. So what ports does this application expose, and what protocols are on those ports? The parameters for talking to it, so things like TLS encryption, as well as service discovery. How do I actually discover where all of these endpoints are? Now, you're probably wondering, why virtual? Were these terms just so overloaded we had to pick some prefix so customers didn't get confused? And that's actually not the case. We decided on virtual very early on because we realized that this was just a mental model. The great thing about App Mesh is these things don't actually exist in your network. What happens is we're able to take this model, these virtual nodes, using virtual services for discovery, routing through a virtual router to other virtual nodes, and we're able to compute that into something that an Envoy can understand and run locally with the application. This ensures that we don't have any of those middle boxes that I talked about earlier, and that we can handle things like TLS encryption in transit, validation, as well as client-side load balancing, all within your application. And so if we look at this customer experience, what do we actually have to do to implement it? Well, we have to take from our customers this API specification. Then we have to convert it into something that an Envoy can understand. Obviously, Envoy doesn't understand App Mesh. And then once we've done that for each virtual node in your mesh, we have to distribute that. And of course, we have to do that very rapidly, ensuring that changes in your API model are distributed down to your envoys within seconds. And of course, we have to do it at scale for tens and thousands of envoys. So if we're actually to rename this talk, it'd be this: configuration distribution at scale. Because that's actually what we have to implement. And that's very powerful that we understand that. If we were to say, only think about this in terms of, we have to build a service mesh, and we did that principal design review, we'd get a lot of network people in the room, and they'd have a lot of great insight, but we wouldn't be leveraging the community of principal engineers at Amazon to our fullest extent. For example, we were able to learn a lot about how ECS does service scheduling, as well as how it distributes tasks and manages their state changes over time, and we're able to take that and build it into how we run App Mesh. So now I want to cover the system design. Now that we understand what our customers want and the experience we have to give, how do we actually deliver it to them? So let's start with a very high-level overview of the system architecture. We run 3 services. At the top, you can see our front-end service that our customers communicate with, where they define those virtual nodes, virtual services, and virtual routers. And at the bottom, we have the service that envoys talk to. And because we're very clever people, we named it the Envoy Management Service. And that service, sole job is to distribute configuration to envoys, as well as integrate with upstream services to, for example, AWS Certificate Manager and AWS Cloud Map. But of course, like I said, customers understand App Mesh, envoys understand Envoy, and so we have to bridge the gap. And that's why we built the last service, the Transformer. Its sole job is to take that App Mesh domain model and convert it into something that each individual envoy can understand. Now, one question I get a lot is, how many services should I run? And I think that's great in this context. Why 3 services? Why not 1? Why not 10? And I personally prefer having as few services as possible, simply because there is some incremental overhead in running more services. But you also don't want to run too few services. And so the things that we think about are, how do we scale these services? For example, the front-end service scales primarily in customer API call rate. The more mutations customers make, the more resources customers create, the more we have to scale out the service. Similarly, the Envoy Management Service has to scale on the number of connected envoys. As customers dynamically change the size of their fleet, we're potentially scaling through thousands of new envoys and having to distribute that configuration down to them. And lastly, the transformer has to primarily scale on the number of meshes you have. As you define new meshes, we have to distribute that mesh to some transformer host and assign computation of it over time. This also gives us some great blast radius properties. If the front end is unavailable for some period of time, envoys can still connect, customers can still scale, they just can't make changes to their mesh. Similarly, Envoy Management Service is down, customers are able to make changes to their mesh, but they're just not able to scale out. And if the transformer is down, customers are able to make changes, envoys are able to receive configuration, it's just a little bit stale. And lastly, this also lets us scale in terms of our teams. Because the Envoy Management Service is so focused on Envoy, we can give that service and build a whole team just around the Envoy experience. For example, when we launched App Mesh, we noticed an issue where changes to your mesh configuration would be loaded into Envoy, and Envoy actually wouldn't be ready to take all of that configuration. It would start routing and send some failed requests. So we were able to make changes to both Envoy and upstream them to Envoy, as well as changes in how we distributed configuration from Envoy Management Service, and improve the overall experience for customers. And obviously, it required no changes in our front end or our transformer. So now let's talk about the front end service. So I'd love to tell you there's something really interesting about the front end, but it's about what you expect. It's a request reply service. Customers make requests to us to create resources, update them, delete them, as well as describe and list them. And so once we've gotten past TLS termination and throttling, we authenticate you. We determine you are who you say you are using SIG-v4 authentication. Next, we compare you, take that identity and load your IAM policies and authorize you. We ensure that you can do what you say you want to do on the resources that you're operating on. Next, we validate that input. And when I was writing these slides, I was thinking to myself, nobody really cares about validation. It's easy. And I actually realized when I was flying here that the reason I think validation is easy for us is because we decided early on to make our API easy to validate. Rather than having fields spread across our API that relate to each other, where maybe setting one field requires you to set another field, or setting this field means you can't set any of these other fields, we made it so that our API led you to properly constructed requests. We decided to replicate fields within structures that define your intent. So say for TLS, ACM integration versus file-based. And that ensures that not only are you able to more easily make a valid request, but also makes validation really easy for us, because we know exactly what context you're operating in. Finally, we persist that. Once we've authenticated you, authorized you, and validated that everything's correct, we have to put it somewhere. Now, at AWS, we're not wanting for database choices. And this is really great. Rather than having to say, here's our database, let's fit our problem to it, we can look at our problem, see what data we're storing, and what kind of queries we're making, and choose the right database for us, whether it's RDS Aurora, NoSQL, DynamoDB, or more specialized databases like time series databases and graph databases. So how did we pick for the front end? Well, we went through our data, and we saw that it was primarily customer configuration and metadata, usually a couple hundred bytes, maybe a few kilobytes for some of our larger structures, but not that much in aggregate. However, it's highly relational. You have virtual nodes referencing virtual services, you have virtual services referencing virtual routers, and those routers themselves referencing virtual nodes. And so it was critical that we ensured the consistency and correct structure of your mesh over time. If you're able to create dependencies and then break them later, it leads to pain debugging why your mesh isn't actually doing what you thought it was doing. And so that all means that we need strict serializability, the ability to ensure cross-key and cross-table that a transaction is atomic and correct. And so based off these three things, we decided that we would actually use an internal database option, JournalDB. JournalDB is a log-oriented database that gives us some really great properties. It allows us to have serializable cross-key and table transactions. And it also allows us to easily scale out our read capacity so we can serve thousands upon thousands of TPS of read requests. And this is important for a service like App Mesh because our customers are frequently querying it to understand the state of their mesh. If you've heard of QLDB, which launched at reInvent 2019, a lot of the learnings and architecture that we built into JournalDB are built on that. So now that we've persisted a mesh, customers have defined their App Mesh in the App Mesh API model, we need to convert that into something that Envoy understands. And I actually think the Envoy transformer is the most important service that we have because it's fundamentally the service that bridges from the customer's declarative view of their mesh into something that actually runs and actually does real work for them. And so that all means that we need strict serializability, the ability to ensure cross-key and cross-table that a transaction is atomic and correct. And so based off these three things, we decided that we would actually use an internal database option, JournalDB. JournalDB is a log-oriented database that gives us some really great properties. It allows us to have virtual nodes referencing virtual services and So the first question we have is, where do we process this mesh? Like many other AWS services, App Mesh is fully multi-tenant. That means that your meshes are living side by side in our database with other customers' meshes. So the first question we have is, we have a set of transformer hosts, and we have to distribute that workload in an even fashion. And so we use a common technique in distributed systems, which is a consistent hash ring. Now, hash rings have a lot of great properties. First and foremost, they're very great at spreading load evenly with some caveats across your network, or your set of hosts. But they have another nice benefit, which is monotonicity. And what that means is, when you add a new host, so in our case a transformer, it ensures that all of the workload moved from other transformer hosts only goes to that host. Similarly, when you remove a transformer host, the only workloads that actually get moved are the ones that were owned by that transformer. So the first thing we do is we set an identifier for each mesh. We actually use UUIDs internally, but those don't really fit on slides. So I've just used the numbers 1 through 8 here. And we bucket them. Now, we actually use many, many more buckets than there are actual workers. And this is important because this allows your hash ring to more evenly spread work throughout the system. If you think about it, if I only used a one-to-one mapping and I removed a worker, I'd only be able to move that workload to some other worker. And that leads to high peak-to-mean ratios in terms of workload. So once we've assigned these meshes to buckets, we're able to put those onto transformer hosts. This allows us to easily scale out. As we add hosts, we can redistribute the load. And if a host gets sick, it stops refreshing its lease over its buckets. And other hosts are able to be aware of that and take over its workload. Now, we always think about failure scenarios at Amazon because we all know they're going to happen. We write our integration tests, we write unit tests, we do canaries, but at the end of the day, the bad thing is eventually going to happen. And so when thinking about distributing workload across hosts, you want to think about various failure scenarios, things like split brain or network partitions. And so in App Mesh, we decided to design our system such that mesh transformation was deterministic. That meant if there was a split brain scenario, we were okay with doing some extra work, maybe processing a mesh on multiple machines and just doubling the amount of work we're doing. This ensures that rather than not processing a mesh and delivering stale configuration for customers, instead, we're able to just take on a little bit of extra workload while allowing our customers to get changes. Now that we've talked about how we schedule meshes to different hosts, we can talk about when do we actually process that mesh. And one option would be event-driven processing. By that I mean, anytime you make a change to your mesh, we then go and recompute the mesh configuration, turn that into Envoy configuration, so we can distribute out the new changes. And this has some really great benefits. It's reactive. When a change happens, you react, compute that configuration, and you're done. It's also really efficient. You're only doing the work you need to. If a customer creates a mesh and doesn't touch it for a year, you don't actually have to look at it again. But there's some downsides here. And again, this falls into those failure scenarios. You can create backlogs of work. So imagine if this transformer service becomes unavailable. And maybe it's unavailable for a short bit, and so it comes back up and it's able to process through the backlog. But maybe we have a longer-term outage. What happens is you end up with this backlog of work that you have to process through. All of a sudden, the work you have to do is bimodal. You have your normal steady state, where you're doing a little bit of work most of the time, and this failure scenario, where all of a sudden you have to do all of the work. And things like inconsistent SLAs, as well as non-obvious are not very well understood behavior when you're coming out of a failure scenario. So rather than starting with an event-driven architecture, we started with a level-driven architecture. By that I mean, we process all the meshes all of the time. Every few seconds, we recompute the configuration for every single mesh. And this has some really great properties that mitigate those failure scenarios that I talked about previously. It's a bounded workload. No matter what's happening, you know exactly how much work you have to do. All of it, every few seconds. Service is down for a second, come back, redo all the work. You're down for an hour, come back, redo all the work. You know exactly how much effort it's going to take to recover the system, because in effect, you're always recovering the system. And that means it's self-healing, not just in these failure scenarios, but also things like bugs. Say, for example, we make a change to how we compute configuration, and it's actually wrong. It's causing customers' envoys to misclassify or misroute traffic. In that event-driven architecture, you'd have to build in reconciliation to ensure that you can recompute those meshes, even if customers aren't actually mutating them. Whereas with level-driven processing, well, you do the thing that you always do. You roll back, and then a few seconds later, everything's recomputed. Now, it is obviously less efficient because you're doing all the work all the time, but rather than starting with an event-driven architecture and building reconciliation, we'd much rather build this reconciliation at the forefront and then layer event-driven processing on top of that. Maybe you slow down the level-driven processing and allow the event-driven system to preempt that level-driven processing. And that's great because if the event-driven system ever fails, well, you just turn it off and you know exactly how much work you have to do. So now we come to computing configuration. We know where we're going to compute the configuration, we know when we're going to compute it, but how do we actually go through and take that declarative App Mesh API model and turn that into something that an envoy can understand? Now, as I said at the beginning of the talk, when you define a virtual node as a source of traffic, you explicitly declare every virtual service that it should be able to talk to. And while it does provide some security benefits, it also allows us to scale out and parallelize this computation. Rather than computing the whole mesh and distributing the whole mesh to every single envoy, we decide to compute just the fragment that those envoys care about. This ensures that your configuration isn't on the order of the size of your mesh, and also that your configuration for your envoys only changes when it's relevant. So how we do this is fairly straightforward. We just take the view from every single virtual node in your mesh and walk the connections. So here I have a simplified view of a three-service mesh. We have a gateway service that depends on a detail service, maybe product items, and then a picture service that both our gateway and our detail depend on. So first, we look at the gateway. We determine things like its service discovery mechanism, its inbound ports, as well as the backend virtual services it subscribes to. We then discover those within our system and find their implementations. I've actually elided the virtual routers here just for simplicity, but you can assume that we're discovering those. And then we find the eventual virtual nodes that back those virtual services. And there we're able to compute configuration for TLS encryption in transit, as well as service discovery. Similarly, we can look at the detail service and compute just its fragment, seeing that it only depends on the picture service and only needs that implementation from the pictures virtual node. Now, if you're thinking about this, I could have a very highly connected mesh where all of my services talk to every other service. And if you did this naively, you might think, wow, you're looking at that pictures virtual service for every single virtual node you have. That sounds exponential, and you'd be right. So what we do is we actually layer a runtime under our transformation. This runtime is able to do things like caching repeated requests to our database, as well as some cross-cutting concerns, things like resource visibility. Things like if you have policies, we can actually ensure that at computation time, those resources aren't visible to the transformation. This also allows us to write very simple transformations. At the end of the day, they're just a few nested for loops. 4 virtual nodes in mesh, look up backends, look up virtual services, and compute the routers and routes and virtual nodes for that. Now, we've computed some Envoy configuration. We call this our Envoy manifest. It includes both configuration that an Envoy can understand, as well as some meta configuration for upstream resources, things like TLS certificates from AWS Certificate Manager or endpoints from AWS Cloud Map. And we need to store this somewhere so that our Envoy management service can take that configuration and fan it out to thousands of envoys. So let's go back to our database slide. Well, what is our data? It's the synthesized Envoy configuration. This scales primarily on the size of your mesh and the size of connectivity of a particular node. And it can range in the size of, again, a few bytes, but it can get up to quite a few kilobytes. However, it's not very relational. It's primarily just virtual node to a manifest. We don't really have to care about all the other virtual nodes because we denormalize the data into something that we can distribute down to a single virtual node. And it doesn't really have to be so consistent. We're OK with eventual consistency, and we don't really need multi-key transactions. We're just publishing a single manifest for every virtual node. So if you're familiar with your AWS database offerings, you probably guessed that we decided to use DynamoDB. DynamoDB is a NoSQL serverless database that is able to scale up to thousands and thousands of read and write TPS. And this allows us to store these manifests in a highly scalable way. And in the future, we can leverage technologies like DynamoDB Accelerator to further improve our read scalability. Now, before I talk about Envoy Management Service, I want to go back to Envoy a little bit. As I said at the beginning, Envoy is, well, it's primarily a layer 7 load balancer. It also is able to do some layer 4 load balancing and proxying. But I want to talk about how we configure Envoy. A lot of proxies and a lot of software is typically configured through static configuration. But Envoy actually exposes this really amazing API called the Aggregated Discovery Service. This is a gRPC API that is open source and you're able to implement. And it defines a way for an Envoy to request information about resources that it understands. For example, listeners, so being able to bind to ports on the host, as well as filters, things that can, say, inspect whether or not the inbound traffic is TLS or not by looking for the TLS client hello, doing original port recovery. So when we do that TCP, or when we do that IP table proxying, we actually send it to a specific port on Envoy, and so we need to know what your actual destination port is. It's able to also do TLS termination, and also HTTP request management. So that's where the virtual routing, that layer 7 routing comes in, where we terminate the HTTP request, and then use routes to match your traffic to a given action. And as well, we're able to dynamically load secrets, TLS certificates, for example. Once you've decided on where traffic should hopefully go, you have clusters. And these really correspond to, in my mind, connection pools. They define things like whether the destination uses TLS and what its validation is, so you can ensure that that destination is actually who they say they are. Things like timeout settings. And they also reference endpoints, whether they're DNS, so Envoy will actually query DNS on your behalf and discover endpoints to load balance across. Or we can actually vend endpoints directly from App Mesh. So if you integrate with AWS Cloud Map, we go through the effort of querying Cloud Map and distributing those endpoints down to the Envoy in a configuration that it can understand. And that's additionally powerful because we're actually able to annotate those endpoints in a way you can't do with DNS. So for example, we can define whether those endpoints are part of a particular deployment or maybe in a particular AZ. And you can actually configure which endpoints should be visible to certain virtual nodes. And while most of this configuration changes with your mesh, right? A route only changes when you change your route in your virtual router, and a cluster changes when you change the virtual nodes that you're connecting to. Others, like secrets and endpoints, have changed much more dynamically. TLS certificates rotate, and endpoints scale as you deploy new revisions of your software. So we had to ensure that not only are we monitoring the manifest changes, but we're actually managing and maintaining the state of those secrets and endpoints over time at a high velocity. So now let's talk about how we implement the Envoy management service. So you have an Envoy, and it goes through roughly the same process that you as a customer do when you make a SDK or CLI call to our front end. We added IAM signing to Envoy, so every request and connection to our Envoy management service is signed using SigV4, and you're able to define policies that ensure that Envoy can only receive configuration for the virtual node that it should receive configuration for. And we go through the same process that we do at the front end. We authenticate you, we authorize you, and we validate that you are talking about a virtual node that is actually in the system. And once we do that, we start maintaining this long-lived state about that Envoy. Aggregated Discovery Service is a streaming API, which is great because it ensures that we're not bootstrapping a new connection every time an Envoy needs new information, but it also means that we have to maintain this state over time. So once we've gone through the process of ensuring that that Envoy is allowed to connect, we first bootstrap a connection manager that manages that gRPC interconnectivity. And then we set up a synthetic Envoy, a state manager that monitors both the last known state of that Envoy and the desired state that we're driving towards. This allows us to ensure that we have a good idea of both where the Envoy is, based on our last known information, and where we want to drive it towards. We're then able to query our manifest manager, so make requests to DynamoDB and retrieve those manifests, as well as bootstrap processes that can make upstream requests to AWS Cloud Map for endpoints and AWS Certificate Manager for TLS certificates. And then, as we discover resource changes or new resources, we're able to compute the diff between what the Envoy has and what it should have, and stream down only those changes. Now, we could manage this long-lived, multi-threaded, concurrent set of processes ourselves, but that's hard. And it's not really work that's core to the problem we're solving, which is delivering configuration at scale. So instead, we leverage akka, which is an actor system based on the JVM. akka is able to handle the multi-threading between actors and make it appear as if each actor is processing one event at a time. Each actor in the system, which is the connection manager, manifest manager, Envoy state manager, and the cloud map and certificate manager integrations, are able to think as if they're just single-threaded processes. Under the hood, akka is scheduling and distributing these messages such that it's able to achieve a high degree of parallelism. This allows us to also redefine how we use these actors together. For example, the connection manager, Envoy state manager are per envoy. We manage those on a connection basis. But things like Cloud Map and Certificate Manager and the Manifest Manager, we're able to leverage across multiple envoys. Because at the end of the day, you define a single virtual node, and that configuration is relevant to potentially thousands of envoys. And this allows us to get great utilization of these upstream services and avoid having to make one-to-one requests for every single envoy in the system, which just fundamentally won't scale. Now that I've talked about how we define the customer experience and the system design, I want to talk about operations and foundationalness. As I said at the beginning, AWS builds services for the long term. And as part of that, we want to ensure that the service is maintainable by the team that builds it. At AWS, we don't have a dedicated SRE team. Every service I build, I operate. I go on call for App Mesh. And because of that, we want to ensure that we're spending as little time on operations and high-severity events so we can focus our time on building customer features. Additionally, we want to ensure that as we're building features, we're able to spend most of our time in the design and implementation phase. Things like deployments, we want to minimize the overhead of that. So App Mesh is built entirely on AWS. And as part of that, we're able to define two key artifacts that really power every part of our infrastructure, whether it's the VPC, load balancers, managed databases, or our application services themselves. Now, we launched at reInvent and public preview, reInvent 2018, in 4 regions. In March of 2019, we went GA in 13. That's a lot of infrastructure. Again, we're talking about VPCs in 13 regions, load balancers in 13 regions, 3 services deployed across 13 regions. We needed to ensure that for our developers to do the right thing in terms of making infrastructure and code changes. We can't afford drift. So we primarily deploy these 2 artifacts. We build container images from our source, and we also generate CloudFormation templates from our source code as well. So we define everything in terms of infrastructure as code. Once we built these artifacts, we deploy them to a staging environment. This is a smaller environment that's still reasonably prod-like, but it ensures that the software can deploy, ensuring that we have the right environment variable set, and much more likely that we didn't have a typo in our CloudFormation YAML. Once we've done that, we deploy to Gamma stages. These are production-like environments that are scaled to production and are constantly maintaining production-like load. This ensures to a high degree of certainty that if it works in Gamma, it should work in production. We additionally run integration tests when we deploy new code, as well as canaries that are continuously monitoring the stability and correctness of our services. We then deploy to the first production region, and we actually let the software sit there for about a day. And that sounds kind of slow, but some problems are slow to manifest. Sure, there's those cases where you deploy code, you see a spike in 500s, your alarm trigger, and you roll back immediately. But other problems are much more pernicious. Say we have a memory leak in that Envoy management service, where every time an Envoy connects and disconnects, we leak a few bytes, maybe a kilobyte of memory. Maybe there's an actor we don't clean up. In the short term, that doesn't look like much on our graphs. Heap memory goes up a little bit over time, but it won't really manifest until we've been running that software in production for hours. This ensures that before we deploy to many regions, that we're able to catch these kind of subtle issues before we have a multi-region outage scenario. As we build up confidence, we increase our rollout rate, deploying to 2 more regions, and further scaling up geometrically. This provides a nice trade-off between pessimism about the correctness of our service, and as we build up confidence in our code that it's able to deploy to regions and run successfully for longer periods of time, that we're okay with speeding up our deployment velocity. Now, even with all that, this looks like kind of a long pipeline. And it'd be really awful if our developers had to spend all of their time looking at this pipeline, approving things through the pipeline, and moving things forward. So we made sure that when we launched App Mesh, we were full CD from the very beginning for our infrastructure, as well as our services. This ensures that the only thing our developers really have to care about is latency for dependent changes. Once you check in software, we build those 2 artifacts, our container images and our CloudFormation templates, and we're able to deploy them through these pipelines. And by running things like integration tests, as well as things like change set comparisons, so observing what CloudFormation is going to do and being able to ensure that that's going to be safe and something that we've seen before, we're able to just deploy code and not really have to think about it. Next, I want to talk about our infrastructure. And hopefully, it looks a lot like your infrastructure. We have a VPC, which has VPC endpoints in it, so we don't have to make outbound network connections. We set up network load balancers for our external services and put those load balancers in DNS records. We actually use 2 DNS records, one for that common external API, appmesh.useast1.amazon.abadus.com, as well as internal DNS that we're able to leverage to give a more programmatic name for our integration tests and canaries. We provision our managed databases. So obviously, we don't want to have to manage databases. That's undifferentiated heavy lifting. So we use JournalDB and DynamoDB. And then we provision our front-end and transformer and EMS services on ECS on Fargate. And if you're looking at the slide, one thing that's missing is a Bastion host. How do I get in there? How do I play around with my services when they're not operating correctly? We actually don't have any Bastions. And we do that because we want to provide security and privacy to our customers. We want to ensure that the only information that's able to be accessed from those systems goes through controlled and audited systems. So CloudWatch logs for logs and CloudWatch metrics for metrics. Now, as I said before, we run everything on Fargate. And I love Fargate. If after this talk you go and do 2 things, first, it's go look at App Mesh, but also try out Fargate, whether you're using ECS on Fargate or now EKS on Fargate, which launched this morning. On Fargate, we run our services with roughly 3 to 4 containers. We define an application container, which defines our services, as well as a proxy, Envoy in this case, because we love it so much that we want to use it for our own services, as well as sidecars that handle logs and metrics. But that's not all we run on Fargate. Fargate is fundamentally a compute primitive that allows you to run ephemeral tasks, whether they're long-lived like services, but also things like integration tests. This is actually a real integration test from our validation test package. It's the shortest one I could find. A lot of them are much longer as they're testing both more complex API structures as well as end-to-end tests. So we're able to actually write cucumber tests that cover all of our example applications and ensure that they run correctly on every deployment. But instead of maintaining test infrastructure and having to patch that and secure that, we're able to just leverage Fargate. When we want to run a test, we put them in containers, run them in our VPC, and then once the tests pass or they fail, we get the result and the task goes away. Not only does this ensure that we don't have to maintain the infrastructure and get away from that toil of host patching and securing the underlying compute, but also means we get to integrate that with our VPC and our IAM credentials. So rather than having to distribute credentials down to test infrastructure, we just associate with our applications. You also get great integration with things like CloudWatch logs, so that everything that comes out of standard out of these tests goes directly into CloudWatch logs and is stored for lookup later on. We're also putting our operations tools into ECS tasks. So rather than, say, deploying ops tooling to your dev desktop or an operations host, we'd much rather have our operations tools versioned in the same way that we do our services. This allows us to, again, assign IAM credentials to those tasks, ensure strict auditability of who and when these tasks are running, and also gain access to internal APIs that we might not want to put on the network, because we're able to just launch that task from a CLI script, connect it into the VPC, and only then are we able to query those endpoints. Finally, I want to talk a little bit about monitoring, both in terms of monitoring the service, but also monitoring your customer experience. As I said before, we run both integration tests, but we also run canaries, covering all of our APIs and as many scenarios as we possibly can. And one thing I always tell service team members when they're starting to go on call is, see canaries failing and the service looks okay, the service isn't okay. When you see failure in your synthetic customer load, and you're not seeing anything in your service, it means you're missing something. So as part of that, I do want to talk about the key metrics that we typically think about when we monitor these services. And I like this mnemonic. I forget who came up with it, but it's a common industry term, and it's RED. Basically, for every service, you look at its rates or its input. You look at its errors, so client errors, customer had misconfiguration, as well as service errors, something bad's happening on our side, as well as duration. How long are those requests taking? And for the front end, this is pretty straightforward. Rate of input is requests per second. If we get increased rate requests per second at our P99 for our hosts, that likely means we need to scale out and distribute that load. Similarly, if we see our request rate drop to 0, that means something bad's happened and we need to react. For failures, or errors, we look at failed requests. And we look at primarily service exceptions. If some request fails on our side, and it's failing for more than 1 or 2 times in a minute bucket, we want to be alerted so that we can look into it and triage. But we also want to look at client exceptions. Again, you have to think about these failure scenarios. If all of a sudden we see a spike in client exceptions, that likely means that we've done something wrong. Maybe our validation code or our feature flag code is misclassifying requests. Additionally, we want to look at throttle exceptions, because that ultimately means that a customer is having a bad day. And so here we use things like CloudWatch Contributor Insights, which allows us to see our top throttled customers and proactively increase their limits. Finally, we look at request latency. And for this, we want to keep it fairly low, usually under 100 milliseconds. Though this can scale as we add more upstream integrations, like querying CloudMap to ensure your CloudMap resources are there, or that your ACM certificates are present. But typically, we want to keep these at the P99 under a second. And importantly, we always think at the tail latency, or tail scenarios for customer experience. If you're looking at average, you're seeing what happens most of the time, but you're not seeing where you're actually failing for customers. So for EMS, we primarily scale the number of connected envoys. Again, this is because our customers are dynamically scaling their fleets. They're adding new envoys, deploying new revisions, and overall, connecting thousands of these envoys to our Envoy management service. When we talk about errors, we're talking about upstream request failures. Are we not able to find the manifest for this virtual node? Are we not able to connect to Cloud Map or ACM? We also look at this in terms of client exceptions. And for Envoy, that's ACKs and NACKs. So whenever we distribute a resource to Envoy, it responds back with either acknowledgement, great, this looks good, or a NACK, which says, hey, there's something wrong with this. And again, we monitor these because that's the overall customer experience. If all of a sudden we see a stream of NACKs based on deployment, that tells us we did something wrong, whether it's bad configuration from the transformer, or there's something wrong in EMS about distributing that configuration. And of course, for duration, we want to look at how fast it's taking us to reconcile those envoys, because this is a primary indicator of customer experience. If it's taking us dozens of seconds or minutes to reconcile that envoy, that means your mesh is in this highly inconsistent state, and you're going to see these Heisenbugs, things where some endpoints in a virtual node are doing one thing, and other endpoints are doing a different thing. And when operating normally, we want to drive to a consistent configuration across your mesh as soon as possible. For Transformer, as I said at the beginning, we scale the number of meshes processed. When we have more meshes in the system, we just scale up more Transformer hosts, and the load naturally rebalances. For errors, we look at processing failures, and we take these very seriously. Any processing failure in the Transformer is an automatic high-severity event for us, because that means we did something wrong. And because of the way Transformer works, that means that it won't get fixed until we figure out what the problem is and roll it back. Finally, we look at duration as processing time. Now, that's how long it takes to process a mesh. Even with the parallelism we built in, bigger meshes take longer to process. But it's also lag. Again, as App Mesh is a multi-tenant system, we're running multiple meshes on a single machine and processing them. So while your mesh may compute in a dozen milliseconds, if there are other meshes on that system that are causing it to get queued up for a long period of time, it may take us more time to actually come back and look at that mesh. And so we want to make sure that, again, end-to-end latency is low, and so we look at that processing time at the P99 as an indicator of customer impact. Now, we have these metrics and dashboards on our rates and errors and duration, and even more fine-grained metrics for key things that we care about on a day-to-day basis. And we put those in dashboards and alarms. But there's a lot we don't know about the service, especially because it's a new service. As we scale up, we learn interesting things about how things fail and how things scale over time. And because of that, rather than just emitting these metrics, we actually emit full observability events for every request in the system. So for the front end, any API request. For the transformer, every mesh processing run. And for EMS, metrics and observability events about reconciling each individual envoy. And we put those into CloudWatch logs, and we're able to query them through CloudWatch logs insights. CloudWatch logs insights is a really great way to dynamically understand what's going on with your system at any point in time. Rather than having to figure out what you have to know at the onset, you can instead emit these observability events, generate hypotheses, and dynamically query your data to either confirm or deny your guess about what's going on with your system. So to summarize this talk, I would say you should, and when you're designing services, I think you should remember these three key things. First, you want to work backwards from your customers' needs and user experiences to understand what you need to build. Again, you don't know what's under the hood until you know what kind of car you're building. Second, I would say design your system with purposeful services that can scale independently, both in terms of technical scaling, but also in terms of your team and organization, and are resilient to the common failure scenarios you expect for your service. Finally, leverage immutable infrastructure as much as possible so that you can reduce your operations burden. And also, monitor key service level indicators that read a mnemonic, rate, errors, durations, to ensure happy and healthy services. Okay, thanks.